thank you, by the way, Konstantinos, very much for meeting with us today, and I'll just turn it over to you, please. It's all yours.
Thank you, and thank you, of course, for the invitation. I'll share my screen now. Let me share this. Okay, classic Zoom question. You can see
we got it, audio and visual.
Cool. Well, hello everyone. I'm gonna make this full screen.
That would be good. Yeah, it looks good. Thank you.
So, also I'm writing on the thing. You can see this high, right?
Yes. Cool. Don't scare me like that, though. That's a Zoom bombing technique.
No, that's just me. Okay.
All right.
So I'm going to talk about these acronyms here. QNLP stands for Quantum Natural Language Processing, and NISQ means noisy intermediate scale quantum devices. So this refers to the quantum computers that are available today, and they're very noisy, as in the quantum information does not remain coherent for a long time. So you have to do, let's say, all the operations you want to do as fast as possible before noise comes and kills your computation and makes it pure noise. So this talk is about what can we do about natural language processing, or for natural language processing, with the very bad prototypical devices we have today. And I have to say that I am based in Oxford, and I'm supported by this very nice fellowship by the Royal Commission for the Exhibition of 1851. And mainly the QNLP research that I'm doing is commissioned and supported, and I'm doing it for Cambridge Quantum Computing, and I'm going to introduce later the other members of my team. And actually, Cambridge Quantum Computing were the company for which I'm advising, who pushed this whole project and were very excited about pushing quantum computing for NLP in general. So I'm very grateful to them for pushing this very interesting field. So let's get to it. So this talk is about, I'm gonna say that this is a slogan that I made up. So it's pretty long. So I'm saying here, from word to sentence to diagram or tensor network to quantum circuit to NISQ device. So it's okay if all or neither of these terms make sense to you. I'm gonna go through them in the following slides. I just want to say that from word to sentence is the book title from the late logician Joachim Lambeck, who introduced the grammatical models, the grammatical mathematical models that we're going to be using for natural language processing. Actually, he introduced these models for syntax, and they are a variation of the Chomskyan models, the context-free grammar ones that Chomsky introduced for natural language syntax and grammar. But we are going to use Lambeck for reasons that I'm going to explain later. And then from to diagram to tensor network is, it refers to a graphical language that we give to process theories in general, and in physics and computer science. And this is something that Bob Cook from Oxford, who is also the lead in the QNLP project supported by CQC, he introduced these things to quantum mechanics under the name of categorical quantum mechanics or quantum theory. And they actually have a very nice book with Alex Kissinger for people that want to know how you can do quantum theory with pictures. And from to quantum circuit to NISQ device is the implementation practical part of this whole project, where you start from some abstract stuff, and then we try to put it on quantum circuits and actually run them on real devices and see what you can do with these things. So let's get to it. This is a high-level overview of the whole, let's say, pipeline that I'm going to be discussing. So I'll put more symbols to the slogan of the previous slide where I have a sentence, I make a diagram out of it. I'm going to show you what these diagrams look like. We can reshape and manipulate these diagrams to serve our needs and make them look nicer. Then we can instantiate them in terms of quantum circuits. I'm going to show you again how this happens later. And then the last step, the compilation step, is basically, I'm going to call it just a simple engineering step. No, simply call it an engineering step, but it's not simple at all. It in general entails solving a lot of NP-hard problems that are a nightmare for people who do compilation, but you know, someone has to do them. And actually CQC has a very competitive compiler called Ticket, which we used for sending circuits to IBM's prototype devices. So let's start with the NLP side of stuff. And I'm going to take you through this with an example, because I think it's easier like this rather than just talking abstractly about words and you know, types and stuff like that. So take the sentence about Malevich. So Kazimir paints black squares. This is a grammatical sentence in English. And what we call pregroup grammar is a relation that assigns grammatical types. So this N to the R, N to the L, S, they are types in a algebraic model of grammar where these types are composed with this product operation. So putting types together is a product operation, like you do, exactly like you do with numbers or elements of a group and so on. And these superscripts R and L refer to inverses. So usually if you have a group, you have an inverse, which is usually symbolized with a superscript. For example, if A is a group element and A to the -1, if you multiply these two together, -1 would be the inverse, and then you would get the identity element, okay? And of course it would be the same if you do it backwards. But here, the idea is that if you multiply from the right or if you multiply from the left, it makes a difference. That's why we symbolize with R or L the right or left inverse. So the idea here is that Casimir is a noun, so he gets an N type. Paints is a transitive verb, and it gets the type N to the R times S times N to the L. Black is an adjective, it gets this type. And squares, again, is a noun and gets this type. And I've used here this fancy term called monoidal category, but for now all you have to know is basically I have a structure which is endowed with a product structure. So it allows me to plug things side by side, and I'm calling this product, as I did here with some group elements. So how does this help, having two inverses? It helps giving directionality. So you see R here, N to the R, means that because this N to the R multiplies from the right this N, there is a multiplication here, they can annihilate and give the identity. And this wire here, this white wire that connects them, symbolizes exactly this operation, that they can annihilate and give you the identity. Identity I don't draw here. You can imagine it as an invisible type that floats around. So it's like I have N to the R, and they go into something, they get multiplied here, and they output nothing. This is what this wire is. In general, if you have, type 1 or type 2, they will fuse and give you another type 3. Here it just happens that type 3 is the identity, and all I'm left with is this wire, which is this white thing here. Same happens for these things. This multiplies this guy from the left, and they annihilate, and these guys annihilate, and you see only the S type survives. So only the S type surviving is, as we say, a witness of grammaticality. So any sentence for which you can annihilate after you type the words with a parser, every sentence which is typed like this, if all types annihilate such that only an S type remains, and S type is a special type which is called a sentence type, if only the S type remains, then you have a valid sentence in the language. So these reductions, as they're called, these annihilations are called reductions for the sentence. They are morphisms in this category. So category is basically a bunch of objects, a set of objects, along with a bunch of arrows that symbolize transformations between them. So here the objects are types, and arrows are morphisms. So these and arrows are reductions. Sorry. So the reductions are these annihilations, and basically you can see this. You can see the witness of grammaticality as a morphism from this complex typing of all the words together, which reduce to an S. So I have some complex string of types, and then it gets reduced to an S type. Okay. Are we okay so far? Are we? Any questions? Is everything clear?
Any questions, comments, folks?
I have a question.
Yeah.
Hi. So in this case, if the sentence, if we don't have a verb in a sentence, for example, in an exclamation, then according to your theory, we don't have a valid sentence, okay?
If I have an exclamation.
Without a verb, a sentence without a verb.
Oh, I see. Like, do you have an example? Like wolf or something?
Oh, beautiful. Wow, for example.
I see. I see. This is a good question. So this would be part of discourse analysis, I think. It's more of a pragmatics. So yeah, it's not a grammatical sentence. Like if you go to learn English properly, like the Queen's English, they will tell you that a valid sentence is not one without a verb.
Okay.
You can't make, but of course they convey meaning because of pragmatics, right? So I'm going to mention something about pragmatics later and give a reference, but I have to say that this is a bit, let's say, it's a complicated project, which I consider it to lie a bit above what we're doing here. But we are actually working towards this. At least some members of the team are. So what you're referring to, I think, is an instance of a language game in the form of Wittgenstein. So for example, you can make any words mean whatever you want if you use them properly, and everyone in a community that uses the language is part of a social contract, and they all agree to the meaning of words, right? So, I mean, I can imagine a language that has no verbs and everyone communicates fine, right? People point to stuff and they say, like, you know, food or drink or hunt, you know, fire, danger, only nouns. So I'm guessing that for any context like this, with the right pragmatics, you can invent the correct typing so that you can make your formal language work. I don't know if I answered satisfactorily, but it's a complicated question.
I got it. Thank you.
It kind of points to the core of the challenge for NLP, and maybe what we should be doing. And I've been exposed to NLP, you know, a decade or so ago.
Yeah.
And, you know, maybe what we should be first doing in addressing the problem, if you will, or the challenge, is that, first of all, think of it as NLP, where we've got the formalities of the language, the syntax and all that good stuff, like a computer language that's quite well defined. And then you have this other layer of human communication that kind of lays above language, you know, like Jolly said, you know, that doesn't have a verb, you know, so it's like a communications layer, and then there's the language layer.
Exactly, yeah. There's the pragmatics layer, there is
pragmatics,
sarcasm, there is humor, there is poetry, there is slang. All of this stuff is much harder to capture formally than just pure syntax. So I guess we're just making baby steps here, and the pragmatics would be like the ultimate holy grail of NLP, right? If you manage to make a computer get slang that teenagers speak, then, you know, you've done something really, really hard, in my opinion.
So right now, would you say that the research in the industry or what have you is really letting alone, you know, avoiding to make progress in the science, avoiding the pragmatic layer for now and focusing in on something that we could actually solve, perhaps? Is that the way to think about it?
This is a good question because it's not that there is only one route in NLP in the industry. So also because I'm a physicist and I got into NLP recently, and I had to see kind of the history of it to see what to start reading first. So what I noticed is like a parallel to the whole AI business. So people started doing symbolic formal stuff in the beginning, you know, from 50s to late 80s, 90s, right? And then they thought that you could do everything formally and symbolically, like good old logic. Then neural networks came, right? Because even though they were put on paper since 50s or whatever, but then practically they became realistic only very recently, right? Because we have GPUs and a lot of computing power, which is cheap. So I have to say that what we're doing here and the models that I'm going to be promoting are trying to merge the two. So one is the formal aspect and the other one is the distributional, statistical, I don't care about formal aspect or approach of neural networks. Of course, people that train neural networks still haven't managed to make them understand slang, right? So it's another open question if, you know, all these nuances and pragmatics of language, are they just about putting enough training time and resources, computing resources, and then eventually the computer will get humor and slang? Or is it that our models really need to be, let's say, updated significantly? We need the breakthrough. And what we are promoting here is basically a marriage of the two. We want to have flexible models that marry both formal aspects and statistical aspects of that don't care about structure. And the idea is that the models will be flexible enough to capture both, capture language when it's in its most formal and structured manifestations, or when it's totally when the meaning is totally when the meaning is inferred only by pragmatic considerations, say. Does that make any sense?
I'm following you.
Yeah. Great.
Yep. Yeah.
Okay.
Thanks. Very clear.
Okay. Okay, back to our okay. Since we did a lot of philosophical discussions here, let's go back to this very simple and after all of this philosophy, very simple and simplistic, I have to say, mathematical model. So we have types that are assigned to words, and then only the S type remains. So you can imagine that the processes flow downwards, right? All the processes are going to be drawing, they flow downwards. So you can imagine that I have initialized or input some words, they get types in this part of the process, then the types annihilate in this part of the process, and then the output is just this output type, which is S, right? This is what's happening here. So you can imagine that this S just flows downwards and survives. So this is Bob, and Bob is a professor in Oxford who started this whole business of marrying this formal language model with distributional representations or vectorial representations, say, of words. So the idea is that what I showed you before can be seen as a high-level process like I drew before. So words go into the grammar. So words, you prepare some words, they go into some grammatical structure here, and you have an output which is the meaning of the whole sentence. So grammar is tells you how you combine the words in order to make a sentence. Okay, grammar is a process basically, or the piping through which the meanings of each word flow to spit out from the exhaust pipe the meaning of the whole sentence. So Bob developed this with Mernouche and Steven, and you can find everything you need to know to start getting lost in this Zeng-Coecke literature. Zeng-Coecke is an acronym for categorical, compositional, distributional model. So you see they're trying to combine both the compositional, formal, syntactical aspect and the distributional, as in I'm giving distributional representations to the word meanings. So let me introduce some notation here. So I'm going to be talking about states, effects, processes, tensors, stuff like that. And it's very useful to just think of vector spaces for now. I'm pretty confident that almost all of you would know what vector spaces are and how you use them and how you manipulate them. So if at any point this is not clear, just stop me, because then it just means I'm not familiar with the level of the audience. But I'm just going to continue and say that I'm going to be, I remind you that processes flow downwards, right? So this is a state here. This is a state, and it's symbolized by a triangle, because there is no input wire to this triangle and there is an output wire, right? So you prepare a state, and then this is a vector. An effect is a state which is flipped, mirror flipped horizontally. So it has an input wire, and this is an effect, or a test as they call it in process theories. So if you have an input state which flows into an effect, you get a number. So if you have a diagram without open wires, it's a scalar. It's just a scalar of the field that you're using. So if you're using complex numbers, it's just a complex number. If we are using the real numbers or naturals, it's that, just a number. Now if you okay, let me say that my background is I did my PhD in condensed matter physics, and there all of this notation is basically the state of the art in describing many-body quantum systems. But of course it applies the same to any vector representation of any problem that you use where you have to describe many-body states. So how do you put the states of many systems together? So these systems, if you're doing condensed matter physics, they would be like spin states or electron states. Here we have words, right? So how do you put a lot of states together? Well, you can trivially put them together like this. So there is a product structure, as we said before, and this we call a product state. So we have independent states, and this is a many-body state because it has many input many wires, right? A many-body state which is generic, we will symbolize like this, right? And you see, this is entangled, as we say in quantum mechanics, or if you're doing classical physics, you just call it non-separable. So basically, if you have some correlated state, some distribution over many variables, you just symbolize it like this. So these things are not isomorphic to these things. You cannot decouple this triangle to many small triangles. So basically, this says that it's genuinely a many-body state, and that there are non-trivial correlations between these output wires that symbolize individual systems. So I'm just going through notation, okay? So there are two special states and effects. So this is a very special state, and the maximally entangled state. It's just a bent wire, so which you can see as an no input, two output wire. And this is a maximally entangled effect, which has two inputs and no output. And of course, they satisfy this snake equation, as we call it, right? So if you plug them side by side like this, it's like a trivial wire flowing downwards, which is just the identity transformation, or So in general, a transformation is basically something that has some input wires. It will be symbolized by a box and will have some output wires. So this is just me introducing notation. And if you use this notation to say, I had my grammatical structure, I'm going to start giving meanings in the form of vector representations to the words. So every word carries its meaning or semantics in terms of a vector or tensor if it has more than one leg. So the nouns are vectors because they have one output leg. Adjective has two output legs. It's a state with two legs, so it's a matrix. And paints has three legs because it's a transitive verb and it has three legs. So you will see that these legs are between different words. They are connected by these grammatical reductions that now just become maximally entangled effects. So in the context of quantum computation, we will see what this means. In the context of just I have some vectors and tensors, it just means I'm doing tensor contraction. So after you do this, all these tensor contractions, then you just have a big vector, right? Because I have only one wire flowing downwards, the S wire, and this whole thing is the state of a sentence, right? And it's a vector because it has only one wire flowing outwards. So these D subscript with a type are basically the dimensions of the vector space that is carried by the wire for every type, right? So here I had, if you remember, an N type, and here I had an N to the R. So there is an N type flowing here. And once we go to the, once we use the discocant model to instantiate vector representations for the meanings, then you say that every type carries a vector space. Okay, any questions until now? Is everything clear, what I did?
Seems okay.
Okay.
Yep.
So classically, people would fill these vectors. I mean, you could ask, what does it mean to have the meaning of a word represented as a vector? Well, they used to do something called co-occurrence counting, for example. It's a very simple thing to do, where you take a word and you pick a basis, which is the words around it in a context window, as it's called. So like, say, the 10 words to the left and 10 words to the right, there is a window around every word. And in that window, you count how many times that word appears in the context window. So then by counting these frequencies, you will build vectors of co-occurrence. And of course, you can do the same for tensors. So then the idea is that you plug these tensors together, you contract, and then you get, by compositionality, the vector embedding of the whole sentence in a DS dimensional vector space. So for co-occurrence, it's not important for this talk. If you have more questions about how it works, you can ask me at the end. I'll be happy to show you by like drawing some symbols on the slides, but it's not important, so I'll move forward. I just mentioned it because that's how they used to do this classically. But the point is that these dimensions, they grow very large, so it becomes a bit impractical to do this classically, and that was one of the motivations to go quantum. So Will Zeng and Bob Coecke here, in this reference, they said, okay, since these dimensions grow huge in practical applications, how about we use the fact that Hilbert spaces in quantum computing grow exponentially? So as we know, or as maybe you've heard, quantum states are represented on qubits, right? Because quantum computers work with qubits, quantum bits, and because the space which the computational space, which is defined by, say, n qubits, has dimension exponential to the number of qubits. So d is the dimension of the space, and 2 to the n is the dimension of n qubits, right? So if you have 2 qubits, the space is 4d. If you have 4 qubits, it's 16, and so on. So you see it grows pretty large. So they said, why don't we take advantage of this to encode these huge high-dimensional vector spaces and see what we can do if we can get an advantage. And, you know, assuming that you have an efficient way to encode classical information in quantum devices, which is a very, let's say, very hard challenge with near-term devices, or what we have available now, they managed to show that you can get a quantum speedup in a certain task called phrase similarity that I will show how it looks like later towards the end of the talk. But for now, just take it as a motivational. Take this thing as motivation for why to go quantum. So quantum theory gives us two things for free. It gives us a tensor product structure, because this is the compositional structure of quantum theory, and because of the compositional structure of quantum theory, we get exponential Hilbert spaces or vector spaces. It's just a fancy word for the vector spaces in which people describe quantum states. These spaces have exponential dimension. So we get these two things for free: compositionality and exponentially big spaces to work in. This is the take home here. If you want to know more, I really suggest this paper, this paper that actually spawned the whole research on QNLP that we are doing now. So let me show you how we can manipulate these diagrams first, and then I'm going to show you how we go to quantum circuits. And when I talk about quantum circuits, I think you can interrupt me and tell me what is not known for quantum computing, so I take it slower. So one of the manipulations you have to do to obtain to regain your speed up is reshape your sentence. So these wires, you can bend them at will. Bending the wire is allowed because of the compact closed structure of quantum theory. This is basically because of the snake equation that I was drawing before. And because this is true for the states and effects, you can bend the wires around. So if you bend the wires around, you can reshape your sentence like this. So this is a reshaping that was needed in the previous reference of Will and Bob, but Stefano and Niccolò, who have their own company called Hashberg, produced some code that does this automatically. So if you give it a sentence with a pregroup parsing, it finds a bipartite graph where the sentence is reshaped like this. And then basically you see what you do is you convert by 180 degrees rotation states to effects. And by doing this, you reduce the width of your diagram. And this helps in sending it to quantum circuits. So it's supposed to help the compilers to have reasonably sized or reasonably shaped inputs so that you make the compiler's life easily. And the compiler's job is to take a diagram like this and set it to a quantum circuit. And we'll discuss this a bit later. Another reshaping you can do, which is what the CQC team did, notably Alexis and Giovanni, who are part of the team that I work with, along with Bob. They used an argument and an algorithm from Antonin here, where basically Antonin argues that what you do is you take a typing which has adjoints. Adjoints, we call these types that have superscripts R and L. And if you have the superscripts, what you do is you use the state process duality, right? So this whole thing you replace with this whole thing. Because you can always do this, you see you have types that outflow from the box that don't have adjoints anymore. So then, now that you have this snaky sentence, what you do is just yank the wires and you obtain something like this, which looks more circuit-like, right? It doesn't have loops, it doesn't have snakes. It looks like a directed circuit, and then you're ready to map this to a quantum circuit. Now, before we had this mini philosophical discussion about pragmatics, and Alexis and Giovanni, the guys that I showed here, they, together with some people from Tallinn, they introduced the concept of functorial language games for question answering, right? So they went towards pragmatics more. So people that were interested in the discussion we had in the beginning of this talk, I suggest they go and look at this, because they bring the open games framework from Jules Hedges. So it's game theory in terms of diagrams, and they combined it with these diagrams of pregroup grammars that I'm showing here in order to describe language games. And of course, we have this repository here that has code that does these transformations. So it introduces these boxes with the snakes and then remove the snakes. And actually, this is the library that we used. You can find notebooks there with our implementations of the quantum machines, and you can play around with it. You can clone the repo, you can do what you want. And they also wrote an accompanying paper together with Bob, where they show a lot of details about this library. So this should be enough information for anyone interested to dig in and play. So to recap, what we did is we took sentences, we gave them types, we took diagrams out of it. Okay, that's all I've done so far. And these diagrams are process diagrams of states and effects. Okay? Okay. Now, let's go to quantum circuits. And here, please interrupt me if stuff is not clear. So far, I just had some states. So this is a quantum state. You can see every line as a qubit line for now. That's okay. And every word, you can imagine that it has some parameters associated to it, some parameters set theta. And what I'm doing here is that I'm representing a state as a preparation process, which is this box, which acts on a trivial product state, a trivial reference state. So in quantum computing, I'm using this notation, which is a notation from the ZX calculus, which is just a buzzword I'm throwing out there. If anyone is interested to Google, it's a full, complete graphical language for linear maps and quantum theory, and people use it to simplify T counts and reduce resources in quantum circuits. I'm using it in other classical problems like constraint satisfaction. There's a lot of stuff here. So it's called ZX calculus. I'm just throwing it out there for anyone interested in Googling into falling in a rabbit hole. I'm just using it here for notation, and I'm just going to say that this is this state. It's the zero state in Dirac notation of a qubit. So I have a bunch of qubits flowing in the zero state, initialized, and this here will be, generically it will be a quantum channel that prepares the state, the many body state, the many qubit state of a word, and it's supposed to encode the meaning of the word, the vector representation of the meaning of the word inside Hilbert space. And the idea here is that we take the simplification that this is a unitary transformation, and this is how we're going to continue. So any questions until now? Because this is, I haven't said anything complicated, but please stop me if this is not clear.
Sadi, may I ask a question?
Mm-hmm.
For example, by this word theta, you mean, for example, a verb that has three stick in the bottom, yeah? Something like
Well,
this.
I've put here dot 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 to say whatever many wires, however many wires, I'm going to prepare this many qubits here in the 0 state. So if you plug a lot of these things together, so if I have 2 of these things together, it's this state. And if I have 3, it's the 3 qubit 0 state, and so on. And then I have this matrix, acting on all of these qubits, and this is just going to be a quantum circuit or a quantum channel. And here the output will be a state on many qubits. How many qubits is basically the number of legs. Okay, and the job of this box is to prepare that state.
So it means that any word can be represented by a many-body state.
Quantum state, exactly.
Quantum state.
Yes.
Oh, okay.
Yes. And the classical control parameters that control what this transformation is this set of thetas. And they are classical parameters, like control knobs in your laboratory.
Okay.
Is that clear? Okay.
Okay, thank you.
Okay. So yeah, as I said, every word has its own parameters, right? So I showed you how generically you have a box that prepares states, and it has control knobs. If you're in the lab, you have some knobs, and according to where you set your knobs, you just prepare different words or different states, correct? Every word has its own, is characterized or defined by its own set, setting of knobs in your laboratory that prepare different states. Okay. So what is in the boxes, okay? How do you prepare some states efficiently on a number of qubits? So efficiently means my circuits, I don't want them to be very deep because noise will kill them, but I don't want them to be very shallow because they're going to be creating kind of boring states. So a motivation a motivation from quantum machine learning, which is the whole literature, it tells me to use this type of structure for the processes that prepare my states. So again, I have a bunch of zeros going in, so ket zeros, and then this L1 layer acts on them. This box is a Hadamard transformation. So it's the matrix that looks like 1/2 minus 1, right? It takes you from the 0-1 basis to the plus-minus basis. So from the eigenvectors of the Pauli Z matrix to the eigenbasis of the X Pauli matrix. So, or to say differently for people that are really at an introductory level, here I'm creating a vector. This whole thing is a matrix composed of smaller matrices. The gaps here are tensor products. So this guy is here and here and here and here. And tensoring by itself, you're creating this first layer, which is a big matrix that acts on this vector and spits out another vector. Then they have to go through this layer. And this layer is basically a bunch of controlled Z rotations. So if one of the qubits is 0, the other qubit doesn't get rotated. If one of the qubits is 1, the other qubit gets rotated around the Z-axis of the Bloch sphere of the qubit with the angle theta, right? So here, these angles theta are my classical control parameters, my knobs of my laboratory. So this is the internal structure of one of the layers. And then I have the option to put another layer. And this one has its own set of thetas, right? There's set 2 in here. And I can have LD for depth D layers, right? And this has the set theta D. So this whole thing is the word box, the word preparation. And I've chosen this more fine-grained structure for it to have more control over it and to know exactly what it looks like so I can send it to a device. So this we call a circuit ansatz, a parameterized quantum circuit ansatz. And it's a choice. It's a choice kind of ad hoc that we make in order to give space to the words and in order to constrain the Hilbert space and use it as to take more advantage of the Hilbert space as we can to encode our meanings, but not have an inefficient representation and get lost in this exponential space and then be inefficient and wait forever. Is that clear? What I've done here? What I mean by I've chosen an ansatz?
For now, yeah. I think
Okay.
so.
Okay.
Anybody else?
Actually, one more question. I don't understand CZ theta. CZ is a control Z. So theta, how do you mean by theta here?
Okay, so the matrix of a control Z looks like 1, 0, 0, e to the I theta.
Oh, okay.
And it acts on a qubit state, you know, alpha, beta, right? This is the state of a qubit. If alpha is 1, beta is 0, we have the 0 state. If alpha is 0, beta is 1, we have the 1 state, right?
Yeah, but with an extra phase.
Yeah, so this is a control Z matrix.
Okay, great, thank you.
Okay. Okay. So, this is just a note to say that the ansatz that I've used is this is what it looks rotated 180. It's kind of a trivial statement to make, but it's kind of useful to know what your circuits look like when you rotate them 180, because sometimes you want to transform word states to word effects because I want to reshape my circuit sometime. It's just a note. And also I want to say that if you look at this quantum machine learning paper from Voite, then there is a conjecture you will find there about the representational power of these circuits. So basically if D, the depth, is kind of deep enough, but not intractably deep, not crazy deep, so it grows as the log of the number of qubits, then it's supposed to be that it's classically hard to simulate these circuits. So it's an extra motivation to use these circuits because we can claim that we do something which is a bit hard to do classically. So let's pick some hyperparameters now, and I'm going to show you how we take a sentence which is a bit deformed, like Ross draws snaky spiders. I've deformed to take its width, to minimize its width a bit. And then I have some hyperparameters here that I decide what they should be in order to perform the NLP task that I want to do. So these parameters are basically NS is the number of qubits that I decide I want to allocate for the sentence space. So as we said before, ds is an exponential of ns. So here it's a 2D space I'm giving to the sentence space, just 2 dimensions. Very, very trivial stuff, just to get the idea. For the nouns, I'm going to give 2 qubits for each wire. So the space is going to be 2 to the 2, which is 4, right? I'm doing some trivial stuff here, but you know, I'm being slow for clarity. And Yeah. So, and the depth, so this D is the depth that I choose to give to my ansatz. So how many layers? It's this D here. How many layers I'm going to allow every word preparation process. So this is going to have 2 layers, and this is going to have 2 layers, and this and this. Okay. So as we said, this guy is a 4D space. This guy is a 4D space, 4 dimensions, 2 dimensions. And now we can take this diagram and we replace our ansatz into the boxes. We just plug them in, right? We put meat on our skeleton. And now I have this whole sentence with only one open wire. I have all these 0 states getting prepared, right? Time, as we said before, flows downwards. These are 0 states that are initialized and so on, right? We have these angles, alpha, beta, gamma, delta. There is a set of them for every word, okay? And these words are effects, right? So these things are they are post selections. So this is the effect on 0, this is the effect on 0, and so on. This is the effect on 0, and so on. So the effect on 0 says, you know, you just measure all of these qubits, and if the outcome is 0, you keep that probability, that outcome. If the outcome is 1, you discard it. So it's like it's a conditioned probability distribution you will be sampling from when you measure all of these qubits on this circuit. And by doing that, the qubit that survives that you haven't measured, which flows here, the qubit state that flows here, will carry the semantics of the whole sentence. Is this clear? Seems it's clear.
Yeah, I don't know how to answer such a complicated question.
Yeah. Okay. So you see this thing, it's a quantum circuit, it's valid. It's just have some qubits initialized, it's 0 state, some Hadamard gates hit them, then controlled Zs hit them, then another layer of this thing. Swaps are just swaps. A compiler takes care of swaps, or if you're really constrained in a 1D, then a swap is just a series of C nots. So a swap is control knot, and another control knot, and another control knot, and that's how you do a swap between 2 qubits. So, you know, and then this is a valid quantum circuit, which is parameterized by all of these angles. So alpha, beta, gamma, delta, they are angles, and they characterize the sentence, okay? So, as I said, having a circuit like this, if you want to run it, you need to send it to one of the devices that is available today. An example is IBM Q's devices, right? And I'm showing you here the connectivity of their Paris device that has 27 qubits. Here you see the error rates for single qubit rotations and control knots. So control knots you can only do here. The arrows are the directionality. So which one is the target and which one is the control can be either qubit. So for those who don't know, control knot is basically, this is how I drew it before, right? So one qubit, this is the target qubit. If this qubit is 1, you apply an X gate here, a Pauli X. So you flip this other qubit. If this qubit is 0, this qubit just flows through and nothing happens to it. This is a control knot. So the IBM devices usually can do only these 2 things natively. So the compiler takes my circuit and has to compile it to a combination of gates, which are these C nots and single qubit rotations. So you take my circuit and it spits out another circuit that is composed out of C nots and single qubit rotations. But the constraint here is that it has this connectivity here, right? And you see not every qubit can talk to any other qubit. So for example, if you want qubit 5 to talk to qubit 10, you have to swap, do your thing, and then swap them back, which is very annoying. But you know, you have to live with it. The compiler has to do this job. They have to optimally send your circuit to run on such a device so that under these constraints, the depth of the device is not too deep, because every operation has an error. And the more operations you do, the errors accumulate. And because we don't have fault-tolerant computers, i.e. error correction, quantum error correction has not been implemented yet, but at least we know that quantum error correction is theoretically possible due to Aharonov and Shor and others from the 90s, then, you know, we hope that it's just an engineering problem, and then we just do what we can do best with the devices we have. I'm just saying here that, again, we use Ticket by CQC. Here's a reference on Ticket and its performance, and there's new papers on Ticket recently that I haven't cited here. There's a new paper on a full stack benchmarking. But this is me saying that a compiler is really something which is fundamental in actually running something. So theoretically, I can say whatever I want, but if I cannot run it, then it's a bit of a shame. So a good compiler is really, it makes a difference between being able to run or publish something, or just running random stuff and getting noise. Okay. So what can you do with all of this? Okay, so you can do something like this. You can start, this is what we did. We did something which is a very, very small example of question answering. So what we did is, essentially it's binary classification. So I have a bunch of sentences in a training set here. It's a set where I have sentence I and label I. And the labels are true or false, 0 or 1. So every sentence comes with a true or false label. Then from each sentence, I get a circuit out of it, as I showed in the previous slides, where I choose an ansatz, and I choose hyperparameters for how many qubits each wire of my sentence diagram carries, so that I get a circuit. And then this parameterized circuit, parameterized by these thetas, is sent to a quantum device through a compiler, like Ticket, for example. Then the device, you sample from the device, and you measure that qubit. You measure the S sentence space qubit. And the sentence space qubit gives you either a 0 or a 1 with some probability. So probability to measure 0 and probability to measure 1. That's what quantum computers can do for you, right? They allow you to sample from distributions that come from preparing states, measuring them with some effects or measurements, and they spit out the measurement with some probability, which is dictated by the Born rule. And here, the qubit the probability of getting 0 and 1 is the probability that the sentence is true or false. We send this probability to a classical computer, and we check whether the label, or this probability, which is the label, the probability of measuring, say, 1 or 0, if the label matches with the training set label. So if the quantum computer says with confidence, with high probability, that the sentence is true and the label is false, then we change the parameters. We update them. If the label matches, then it's fine, and we move along to the next sentence. So if you loop around here until all the labels converge, and then what you do is you have a test set. This is what you do in any supervised machine learning task. Here we do it, instead of using neural networks, we're using parameterized quantum circuits in their place. But of course, we use them, as I said before in the motivating section, we use them because quantum theory gives us for free a product structure. And so the compositional structure for the grammar is homomorphic to it. And then we do our whole supervised learning task, and a test set is basically new sentences composed of the same vocabulary Of course, the same grammar, otherwise it's garbage, right? And then you get a new sentence that the computer hasn't seen before, but it's made up of the same words. And then measuring the new qubit, measuring the sentence qubit, will give a probability of 0 or 1. And then this will be the truth value of the sentence that the computer has not seen before. So if you want to know, for example, you know, if you're feeding in Wikipedia about philosophers and political theorists, then Giovanni will ask the computer, you know, he will run the circuit that represents the sentence Chomsky is an anarchist. The computer will say, you know, probability of 1 is pretty high because yes, Chomsky is an anarchist. And then Alexis will be happy because, well, he's very sympathetic to socialistic theories. So I've written a Medium blog post that has a high level overview of all this story, but this is more or less as I described it now. It's what's in the blog post as well.
I have a question.
Yes.
If you go back to the previous slide, how do you prepare the classical state from the quantum when you're moving it from the quantum to the classical computer? What kind of encoding do you do? Like, do you amplitude encoding? What do you do?
Wait. So you're looking at this one?
No, from the estimate to you going to the classical computer, you're sending the information, right? So how do you put the classical state? Do you do some kind of amplitude encoding? What do you do?
Right. So this is because we want to avoid doing amplitude encoding. This is we are learning the parameters so that the labels match. Right? We don't encode in the amplitudes some word vectors that we have. We hope that the parameters are learned so that every state is prepared so that the task that we want to do has some satisfactory performance, right? We have a cost function here, as you do with any supervised machine learning task. So no, we don't do amplitude encoding. Actually, this reference here by Zeng and Coecke, which was the first QNLP paper that uses pregroup grammars, this one here, this it assumes amplitude encoding because they want to do amplitude encoding of the classical vectors and then do some Grover style closest vector estimation in order to do sentence similarity, and I'll show later what sentence similarity looks like. But because amplitude encoding is very, very expensive, we chose to do this quantum machine learning style approach because it's shown to have good performance in other tasks like quantum chemistry and other NISQ applications. Did I answer your question?
Yeah, partially, but still I'm not clear. How is the information shared if you don't do some kind of encoding, right? You have to have
so
happening.
The encoding part is this arrow here. From the sentence, you get a circuit and there are some thetas. Then what you do is you measure your qubit to see the truth value. If the truth value is what you send to your laptop. The truth value is sent to your laptop so that the laptop computes the cost function.
Okay. So you're measuring that and getting the classical.
Yeah, exactly. So the quantum computer gives you classical probabilities, right? The classical probability is sent to your laptop. The laptop classically computes the cost function and classically does this update or learning, and then you send it back, you prepare another circuit and estimate again. And you do this until you converge and you're happy that all the labels are matched in your training set. It's just binary classification with supervised machine learning.
Yeah, makes sense. Okay, you're doing all the objective and the loss function in the classical.
Exactly, yes.
Thanks.
Cool. This is what sentence similarity looks like. So let's say you have kids play ball and you have apes are social. And I've done this here. I've connected the wires, the S wires of the two. This is type N, N. So now I have a diagram which has no open wires, right? So it's a scalar, it's a number. The quantum computer would give me basically the cosine, the probability that the cosine similarity between these two vectors is small or not. So I can estimate after I've encoded or learned some states or tensors, I can estimate this thing, which is nothing other than, you know, this thing is just a vector, psi going in. This thing is an effect, phi. And the quantum computer will give me this probability, which is, as we all know, this thing, which is a real number between 0 and 1 because it's a probability. So if it's 0, if it's close to 0, it means that these sentences have nothing to do with each other. If it's close to 1, it means that these sentences are similar in meaning. For example, kids play ball with computers run code. It should have a lower overlap than this one, which says kids play ball is similar to apes are social. So this is the task that was done in Zeng, and they proved that there exists a quantum speedup if you can do efficiently amplitude encoding with a quantum RAM. But this is something that we aim to do in the future with our quantum machine learning approach, and actually do it on a quantum machine. So actually we wouldn't do this for 2 sentences. We would do it with the example that Will and Bob have in their paper. So we would have kids play ball, and we would have this black triangle or red triangle, and here we would put the word for politics or sports or I don't know, science and so on, and we would see to which category this sentence belongs the most. And you can see this as a sentence classification, but the classes are more than 2. So before I had binary classification with supervised learning, and the 2 classes were truth labels, true and false. Here I can have more classes, and I can do a bit more sophisticated NLP tasks like this.
Is it like equivalent of the co-occurrence matrix we use in the typical classical machine learning to do NLP? You're replacing that with this, with a projection metric. You're projecting one vector with the other, I guess.
So in this model, the co-occurrence vectors would be these triangles, and these tensor contractions would be the operations that you would do on your co-occurrence verbs, co-occurrence vectors and tensors to get out a scalar. So instead of doing it with co-occurrence vectors and on a classical computer, we would either train our quantum circuits that prepare these triangle states to predict the correct co-occurrence probabilities. And then, yeah, that's what we would do. We would train these states, these parameterized quantum circuits that prepare these triangles to produce the correct context probabilities as the co-occurrence data says. And then we would run this overlap on a quantum computer. So this runs on a quantum computer. Just the overlap.
What if the matrix is very sparse? In case of your classical, you try to remove the stop words and make the matrix more dense.
Mm-hmm.
What do you do here?
So this is something we haven't done yet, but sparsity is good because it means that you don't need your circuits that prepare the states to be crazy deep, right? If the tensors are full rank almost, then that means that the state could be anywhere in Hilbert space. But because they're sparse, it's the analog of the philosophy of the small corner of Hilbert space in condensed matter theory, where you say, sure, Hilbert space is huge, but the physically meaningful ground states of materials whose properties we want to know, they can be efficiently representable in terms of low-rank tensor networks. And that's what we would do. The ansatz that prepare the triangles would be shallow circuits that prepare a sparse, well, it's a bit misleading to say sparse for quantum states, but its classical representation, the quantum states classical representation will be sparse. And that means that the circuit that prepares it is shallow. And so it's kind of friendly to NISQ devices at least. Does that make sense?
Yeah, it makes sense. Thank you.
Okay.
Certainly lots to think about. I
Yeah.
put your Medium post a link to it in the chat. So, but it was early on this morning. So if anybody's looking for it, just scroll up in the chat. Very good article, by the way.
Oh, thank you.
Yeah, thank you.
Yeah. So yeah, let me end. And if you have more questions, I'm happy to draw some stuff here.
I think you've given us enough to chew on and certainly think about. And thanks for the papers. I'll do my best, folks, to get the links to those papers put into the Meetup message area, because I think coupled with this explanation here, reading some of those papers and circling around to the recording, I think will really pay some dividends, folks.
Mm-hmm.
I'm still amazed, Konstantinos. You're coming from physics to get into this bag of words world.
Yes, there's a lot to learn, and also it's a very fastly, let's say, quickly moving area, NLP.
Are you
the state of the art really changes every 6 months.
Are you finding a growing number of researchers entering into it from the quantum side of the house?
Yeah, actually, we had I co-organized with Bob and CQC people the QNLP conference in Oxford in December. I'm sure I can share a link to that, but it's pretty Googleable, and all of the talks are online on YouTube. And you will see there's a lot of linguists and computer scientists doing abstract pre-group stuff, but also there were a lot of talks of people like physicists and quantum computing people trying out quantum algorithms and see where you can gain speedups for NLP tasks. For example, there was Johannes Bausch who was talking about speeding up voice recognition stuff with Grover. I mean, there's a lot of stuff. Also, Stefano and Niccolò, they're partly working on this stuff as well from Hashberg. We at CQC we're pushing this quantum machine learning approach, but also we are looking at what we can do in the long term as well, with considering that you do have a quantum RAM and fault tolerant quantum computers. So yeah, I have to say I see more and more people getting interested in this, and I'm sure like there's more tasks that I have to discover. There's for example, I was thinking about summarization of text or just generation. There's many things to try out and see what is natural to do on a quantum computer. So That's
So
a
I
good
have a question.
question.
I have a
Finding the
question
task
for you.
which is natural for a quantum computer.
I had a couple of questions. So one
Yes.
is on the, I'm currently working on a project that speech-to-speech like translation or speech-to-speech conversion, one language to the other language, right? So there is a notion, or if you can compare that to the regular way of doing is to do speech-to-text one language, then do text-to-text translation in the other, and then text-to-speech in the second language.
That's right.
That we're trying to do a direct speech-to-speech mapping, right? How can I use some model like this to implement something like that to make things, because of obviously to avoid multi-layer of
Yes.
transformations, to avoid because of the error codes and all.
Yes. Yes. So there has been work on text-to-text translation in these models. For example, Martha Lewis is a name to Google, but directly from speech to speech, I actually am not sure how we would do this.
Here's an answer
There are not many people who are doing that, except one. I think Google has done English to French. Also does not give you high efficiency. So it's a new thing that we are trying to. So I thought maybe you were already doing things. Now, how do you compare the BERT 2 to some of the things that you're doing in the quantum machine learning, the Google's BERT 2 for the classical?
Okay, yes. So this is something we thought. So what is a good way to benchmark what we do, right? So Alexis and Giovanni, the collaborators in my team that I showed before, they argue that the fair way to do this, to compare different methods, is just the number of classical parameters that you use to encode your words and represent them. So we would compare with BERT we would choose a BERT model, BERT-like model, and we would say we choose the number of classical parameters, or maybe the encoding space to be of the same dimension, to be similar to that we use on the quantum circuits, and see which one does better, for example. And also, if we can get away with simulating classically small-scale examples of the quantum circuits, of course, we always do this in parallel as well to have an extra benchmark line, because you can never trust the quantum device to do what it is claiming to do, right? Because they're very noisy and I mean, they're really a pain to work with.
Be nice now. Be nice.
I'm trying.
So in your model, you're assuming no QRAM exists. Is that right?
Yeah. We're just learning the classical parameters of the quantum circuits. So it's all just machine learning with quantum circuits, basically.
Okay,
So
folks.
yeah.
Sorry.
No, it's okay. I was just
Thank
gonna
you.
repeat myself.
Thanks for the questions, both of you guys asked the questions. Yeah, the rest were pretty quiet. Got a couple small ones in the chat, but I think we need to end here. But let me say, if you're still wanting for more, Konstantinos has a follow-up meetup presentation coming up on Tuesday, June 23rd, and that's at 2 p.m. New York time. That's being hosted, interestingly enough, by the NLP community in New York, which is a much larger group than us quantum people. So I don't know if it'll be as intimate as this, but check out the Quantumapalooza site. I've got the details on there. And that's next Tuesday, the 23rd at 2 p.m. New York time. So let me leave it at that. And thank you, Konstantinos, for taking the time out of your, for adding more work onto your regular work. But, part of it is, getting the word out about this technology and getting other people involved in it. Maybe create some competition to yourself of sorts. But it's really effective to get people talking and thinking about this as the broader quantum community is doing, but NLP itself is a real interesting subject that we all can relate to.
Yes. If people join in the other one, there will be some overlap, but I will try to put some more say screenshots from the Python notebooks we used. I'll try to put some more things about co-occurrence, but it will be good to have this discussion again for sure. There's always more things to say, and I see a lot of interesting questions in the chat here, but yeah, okay. Maybe I can answer them later. I'll take a screenshot now and
Okay, that'd be cool. Yeah,
something like this.
we gotta get you off the air here.
Sure.
Yeah, but you know, I don't know how you learn, but I think most of us, many of us, you know, redundancy is good, man. Redundancy is good. So don't worry about that for your next presentation. As I said, I don't know about these folks, but I'll certainly look at the video when I start doing deep dives into the algorithms and such. So appreciate it.
Great. That was fun. Thank you.
Cool. Thank you. Are you okay with these questions here? I got a hard stop because I've got a bunch of 12 and 15-year-olds waiting for me in class.
Oh, I see.
So apologize for that.
I see. So maybe we can take 20 seconds. So like,
Sure. Yeah.
Is an ansatz like a Bayesian prior? Yes. I mean, probably everything is a Bayesian prior if you say I start from that. It is the whole thing is conditioned on your ansatz, but the idea is that you have to make it work with any low depth ansatz which is reasonable. Error mitigation, yes. I mean, in practice we have to do some error mitigation when we scale this thing up a bit, otherwise we'll just be getting pure noise. What else? When practical, and years up to engineers. Oh, that was you. Yeah, we need better computers. Yes. Okay.
Yeah, I put all the burden on the engineers to catch up to you guys.
Yeah.
They're slowing you down.
They are. We had dreams, you know.
You got customers waiting for this stuff. Put a fire under their bellies.
Oh, and I see there is some question about the right and left adjoint, but I think it was answered in the chat. Yeah. Okay. Cool.
Says a lot about you, man. You're leaving no stone unturned. Thank you very much. Appreciate it.
You know.
All right.
OCD with benefits.
All right. Well, have a good day. And you're in the UK presently. Is that where you're living?
Formally, yes, but due to COVID, I am now in Greece. So.
Oh, you're in Greece. Okay. Excusez-moi. I was thinking of Germany, actually, but that's right. You're in Greece.
Yeah.
Well, that's home, huh?
Yep.
Yeah, it's better to be at home. So anyway, everybody, thanks again for dialing in so early in the morning here. And finally, we get it right for the Europeans and, you know, for guys like in Greece and such. But thank you again, Konstantinos. It's been really, really helpful. And if you don't mind, man, I'm going to come back to you in about a year with an update. I want to hear, you know, you running on a 2,000 qubit machine or something. How about that?
Yeah, that would be cool.
Wouldn't that be nice? All right, everybody. Thanks for coming by. Thanks again, Konstantinos. Really, really cool. Appreciate it.